Good morning, everyone. Can everyone hear me loud and clear? Yes? Okay. Um, this is Romi Banerjee, and I'll be trying to help with the Fractal 2 of this course. And it is rather overwhelming to be kind of instructing, if I might put it into quotes, uh, professionals and people who actually know how the real world works when it comes to problems in artificial intelligence. And I look forward to learning from you. I'll just perhaps give an overview of how things look theoretically, and I look forward to learning from you as well. And that's all. And we roughly have about uh, we roughly have about 8 classes in this fractal because we have a Diwali break as well. And we'll try to see how much we can do. The syllabus roughly covers reinforcement learning and 2 topics under probabilistic reasoning. Excuse me. So hopefully we should be able to have that done. And what I have tentatively thought about is I've taken feedback from about the earlier fractal from the teaching assistants that we have. And what we tentatively thought is if we could keep Saturdays for complete instruction and discussion, and Sundays, where the first hour is for instruction and discussion, and the remaining half an hour, which is 9 to 9:30, I will share the syllabus. I will share the syllabus in the slides. And the remaining half of the hour on Sunday, which is from 9 to 9:30, we'll schedule the quiz then. Okay, so what happens is on Saturday we have a full an hour and a half of instructions and discussion. And on Sundays, we'll have 1 hour of instruction and discussion and half an hour of quizzes. Okay, and in the half an hour, we'll start the quiz at 9:05 and you get till 9:15 to solve it and 15 minutes to upload. And within those 15 minutes, we can have some discussions on the quiz questions. Excuse me. We can have discussions on the quiz questions, and if there are any questions that we couldn't answer during the class hours, we could take it offline, which is through email, or maybe we could continue it in the next class. I'll be writing the email on chat. If anyone has any queries, please feel free to drop me an email. Okay, so my email ID is, I've written that down in chat. If you have any queries, please feel free to drop me an email. And you, I suppose, already have the email IDs of the teaching assistants we have. So that should be fine. So now, just like I mentioned, I'll be sharing my screen now. So, right. I hope my screen is visible. I hope that's fine. Yeah, fine. So this is the tentative, yeah, this is the tentative schedule that we have thought, where we have these dates for classes. This is the topic that we try to cover. This is the time that we get. This is when we'll have the quizzes. We'll have 2 assignments, and this is roughly the time that we get as in contact hours for teaching and instruction and discussion. So now the first topic that I just said, that would be reinforcement learning. I have a set of slides which lists all the resources, primary resources that we have actually for reinforcement learning. This is a set of slides of resources. We have video lectures from some very senior professors as well as from younger people who have brilliant methods of explaining a complicated topic. And we have a list of books and articles over here, which I would encourage everyone to read and follow. This book in the second bullet over here, that's the book that we'll be following, particularly for this course. It's a lovely book, and that's that. So this is the resources slide. I'll be sharing it all with you on Google Classroom. And so if we see over here, the syllabus that we have for reinforcement learning will be covering passive learning techniques, active learning techniques, generalization, and policy. And on the probabilistic reasoning, we'll be covering hidden Markov models and Kalman filters. Yeah, there was something on chat I missed. Which chapters? Okay, this will be, chapter 21, which is on reinforcement learning. And for probabilistic reasoning, we will have chapter 15, just a part of chapter 15. Okay, so chapter 21 for reinforcement learning and part of chapter 15 for probabilistic reasoning. Okay. So now I suppose I'll go back to the class now. So right. So in this class, I'll try to introduce what reinforcement learning is and what passive learning and active learning are, and a certain technique under passive learning, and we'll continue passive learning in the next class, which is tomorrow. Okay. So I'll just present. Please feel free to, I'm not sure if you can unmute yourself, but if you have any questions, please put them up on chat. And if I can't answer them during the class, I shall collate them all up at the end of the class and get back to you. Okay. Excuse me. So, right. So now reinforcement learning, if I go to this picture, it's all about an agent that tries to interact with the environment and learn how to go along the environment or how to get by the environment through a series of actions and rewards. So it's pretty much in line with the way we learn from the environment, where we may have particular instructions, or we may not have instructions at all. We just learn by trial and error and just getting a hang of things. And the particular difference between reinforcement learning and supervised and unsupervised learning is that in supervised learning, we learn from label data. There is a supervisor available and we learn from label data. So there are particular classes and categories, and it's all very well placed out. And in unsupervised learning, we try to learn patterns from unlabeled data. Okay, so there is a lot of data available, but in reinforcement learning, it's all about interacting with the environment and trying to gain an understanding of the environment through actions and rewards. At times, we will have proper instructions, we will have proper policies, and at times, we won't have that. This is how it is. So basically, there is a feedback happening over here, which leads us to improvement, which, if I can say, leads us to curiosity, it leads to further exploration. Right. So basically, there's a feedback. Reinforcements could be at the end of the game, they could be during the game, or during anything or an action. And the reward, what is most important over here is if we see this next thing, the reward is part of the input to the agent, and the agent must be wired to understand that the reward is different from other sensory input. So if I can expand this a little bit to acting humanly, if I can just expand this concept a little, recognizing the reward, it essentially means it will give you a sense of success or a sense of failure, which is rather different from what a general sensory input will be. For example, I am talking to you, you can hear me. That's the auditory input that you have, but it possibly doesn't give you a sense of success or failure or a feel good factor. Maybe feel good in the sense that you might enjoy the way I'm trying to explain, or you may not enjoy it. But the success and failure for you over here is, do you understand what I say? Or you don't understand what I say, or maybe you partially understand what I say. So that understanding, that reward factor is very different from the auditory input, just the basic auditory input, right? So this is a very important thing over here. So, and there are certain concepts under reinforcement learning. There must be an optimal policy, a policy which is a rule, a mapping between a possible state and an action. The objective is to maximize the total reward. And like I mentioned, the model of the environment, which is a mapping between state, action, and rewards that could be missing. And we have to learn from our own interactions. So in very complex environments where we can't have a listing of all the rules, perhaps reinforcement learning is a good way to get along with things. And excuse me. And there are certain concepts under reinforcement learning which are very, very important. One is exploration, which is you try to understand or you try to know what the actions lead to. So you do a lot of exploration of the environment, like maybe babies do, the way babies learn. Okay, they pick things up, they throw them down, they put it in their mouth. So they try to get a multisensory appeal of the objects that they hold. They bash things on the floor. So there are some laboratories all around the world who are trying to mimic the way babies learn in order to make machines learn similarly. Now, from exploration, excuse me, I have a bad cough. Exploration leads to intrinsic motivation or curiosity. Rather, instead of leading to, I would say it's something that's intrinsic to every agent. That is, why do I explore at all? I could just be sitting fine and keep myself isolated from all the sensory input. I really don't have to get along in the world. But then it is this what next? It's that curiosity that kind of pushes you on. So, in one way, exploration could be exogenous, which is forced. That is, someone tells you you have a particular goal in mind. And it could be intrinsic, which is you learn along the way. You learn the goal along the way. You maybe maybe divide a certain action into small goals, and the little things that you learn on the way leads to the next thing. So you're curious, you question, what do I do next? Should I pursue this any further? Should I leave it now? So that is again a very, very interesting factor when it comes to reinforcement learning, the reason that pushes you forward, which is curiosity, motivation, surprise. So we could have something that is knowledge-based, some as a function of what I already know, or it could be competence-based, meaning what I'm already good at. So I'm particularly maybe not curious about it anymore. But again, if I'm good at something, I could be curious about how to improve it, depending on how industrious I am. So these are some interesting words and concepts that come under reinforcement learning, and there's a lot of research happening all around based on these individual topics. We have exploitation, eventually using what you learn. There's this exploration exploitation trade off that I have to repeatedly maybe try out something in order to learn. But when do I stop learning? When do I stop the novelty detection? Is it when I get tired, when I lose hope? So these are some very human factors that come into this rather objective world of machine learning. So then again, we have regret. I learn from my mistakes. So then the question that comes is, how do I reflect on my mistakes? Autonomous systems or artificially intelligent systems these days, we are trying to reason, we're trying to reflect, as you might say the word over here, reflect on our failures, reflect on our successes in a bit to improve in the sense it could be self-learning, it could be learning from other peers. Peers could be human beings, it could be machines again. And there is this term that's again coming up, which is consciousness in machines. So it could be a self-conscious reflection where I'm aware of the society around me. I take that into consideration in my learning as well. I look into that. When I have a social agent, when I want to design a social machine, perhaps a factor of self-conscious reflection would be necessary. These are some terms, if I might mention. There's Marvin Minsky's book on the society of mind and emotion machine that has these lovely layers of learning and interaction with the environment and feedback and growing up from there, which is a lovely book to read. And then sampling and difficulty. Again, we keep trying, we learn from our mistakes. So this is kind of an overview of what reinforcement learning is. So we try something out, we learn from it, we don't have particular policies, we don't have particular state action pairs, maybe very explicitly mentioned, and we have a system of learning from rewards, either negative or positive. Positive rewards push me on, negative rewards allow me to rethink or revisit. So now these kind of agents that we are that have been talking about so far, there are different kinds of agents that participate in the learning mechanism. One is the utility-based agent that tries to learn a utility function. A utility function meaning how good my policy is, or how good is a particular action from a particular state. I try to gauge that. I try to kind of arrive at an analysis of how good a particular action is. So over here, we need a model of the environment to arrive at decisions, because I need this action state, a basic idea of the actions and the states, and my purpose is to learn how good this action is, so that I obviously maximize the expected outcome utility, or I always try to follow the best path. A Q learning agent is one that learns the action utility function So it kind of compares expected utilities across available choices without a priori knowledge of outcomes, but it lacks foresight. So it's kind of just this state and the next state. It doesn't have information on the states that follow. That is what a Q learning agent does. So it's rather local in nature, perhaps. And a reflex agent is something that tries to learn a policy or that maps directly from states to action. So this is uh, more like the way we learn, perhaps from the environment. Mostly, perhaps the way when we are babies, perhaps a reflex agent is what we are. So now, before we move on to reinforcement learning, here just a recapitulation of some very basic techniques which are important under reinforcement learning. One is Markov decision processes. This is essentially a mathematical framework for modeling decision making in situations that are partly random and partly under the control of a decision maker. These comprise a set of states. You have a set of actions from every state. You have a transition model that maps state, one state, and action to and the next state. You have a reward function that kind of tells you whether this particular action is good or bad, or how good or how bad it is. And you look for a policy that kind of maps these all together. Right? And these are discrete time, these are stochastic discrete time, meaning they're not continuous, and stochastic, they're random. And the meaning is this transition that we have is just a function of the current state and not that of the previous states and action. This is roughly what a Markov decision process is. So if you have a Markov chain, a Markov decision process is where you have choices and rewards embedded into the Markov chain. In a reinforcement learning problem is where basically this transition model and reward, these two elements are unknown. Okay, so that's the basic difference. So it's good to have a starting point by knowing what a Markov decision process is. You'll be finding this term. Yes, sorry, there's a question on chat. Actually, utility agents and Q agents. Yeah, sorry. So, a utility-based agent, it is somewhat fixed in the sense that it has a particular model of the environment to arrive at decisions. Okay, it needs a model of the environment, meaning it needs a state action, some kind of a transition idea. It must have some kind of a reward idea. It may not have the functions in mind, but it must be having these value pairs, these state action value pairs. It must be having that. Okay, and the Q learning agent over here is it tries to learn the function for opting a given action from a given state. So in a utility-based agent, what happens is it has the entire model of the environment available at its hand to arrive at decisions, but a Q-learning agent is basically between just pairs of states. So it's more of a local decision happening over there, and at times a Q-learning agent helps you converge faster, as we shall see in our later slides over there, that at times perhaps a model of the entire environment might confuse me. I have many action and states to go to. I might be confused, but when I have a Q learning agent, perhaps I shall come to this concept of dynamic programming actually in a couple of slides. That is where I take optimal local decisions to arrive at an optimal global decision. Perhaps yes, we could say that. Actually, Q learning, this is more of a dynamic programming problem. I shall come to this. I have it in the next slide over here, right? So over here, when a utility-based agent is more of taking the entire environment under consideration, a Q-learning agent is more of a local decision arriving at a global optimal decision. And when I say a local decision towards arriving at a global decision, I come to something called dynamic programming. So a dynamic programming technique for solving optimization. Over here, this is an optimization problem, right? Reinforcement learning. I'm trying to find a technique that will allow me to optimize my learning or optimize my rewards, or kind of find the best way to do something, right? So that's the entire premise of what reinforcement learning is. So it is an optimization problem. So a technique for solving such optimization problems that basically comprises an optimal substructure in such a fashion that these substructures or these sub-problems that comprise my entire problem are recurrent or can be reused. That is the technique of dynamic programming. So what do we do over here is I break up my entire problem into smaller problems, simpler sub-problems based on the principle of optimality. That is, I break it up into such a way that the optimal solution to the sub-problems leads me to the ultimate global solution, a global optimal solution. And these sub-problems are recurrent in nature, meaning I can reuse these problems. For example, if I have a Fibonacci tree problem, I have the smaller Fibonacci numbers that contribute to the larger numbers, right? So if I could save these numbers or save these numbers that happen or kind of evaluate at certain particular positions, if I can save them in a way, I don't have to reevaluate things, right? So if I might extend this to the way we behave in real life, when I'm just trying to learn walking, I take baby steps. What happens first is my muscles start growing stronger. When I'm small, as a very small baby, I'm just babbling around, right? I'm moving my hands, I'm moving my legs. So I have these neural connections forming up. These motor connections, motor neuron connections, these sensory to motor neuron connections happening. So that is something, so that's learning at a very atomic level. I'm not aware, no one can tell me particularly, perhaps a neuroscientist might be, that which motor neuron or which sensory neuron leads to what action, right? But so that's learning that's happening at a very atomic stage, at a very, very basic level. So you find babies, they move around their hands, they look around, so they're kind of gaining a model, a representation of the world on their own. They may not have values attached to it. Unfortunately, we're working with a machine that needs some kind of a number associated with whatever action that happens. But there's some representation of the world that we have in our mind in relation to these actions and these little bits of learning. So towards the ultimate goal of learning to sit up and take the first step, we have these basic small problems, which is learning these sensory to motor neuron connections, and we save them for life, isn't it? You don't relearn them unless there has been an accident or an unfortunate circumstance. You don't relearn it. It's all there in your mind. So in a way, I can maybe find an analogy between me learning to walk and dynamic programming. And so that ultimate goal of learning to walk is broken down into these subatomic processes of finding these connections between what sensory input leads to what motor neuron action, and I save them in a table in my in my brain in some form of representation, some abstract data structure, and I keep utilizing them when I walk. So then what happens is this this goal, maybe this evolutionary goal that I have of learning to walk, becomes a rather procedural thing. So I kind of learn on the fly. So I don't have particular transitions in mind. I don't have particular reward functions available. I do trial and error, and I ultimately learn how to walk. So this is dynamic programming in life, if I might draw an analogy. So this is Bellman's equation for optimality. Looks rather weird over here on the screen. I'll fix it the next day. I'm sorry. So here what we say is, if I can maximize the reward with the V over here, if X is the state that I'm starting with, and V is a value or a reward value attached to it, my entire premise is to maximize the reward that I have when I take a particular action from this state to the next state. Fine. And over here, B, the beta over here is a discount or an impatience factor. Later on, we learn and certain other techniques over there that we could have a learning parameter attached to this as well. Learning as a function of how many times I revisit a particular solution, as well as the kind of the frequency, the beta parameter, and certain other techniques it modifies to the learning parameter in the sense of the frequency. Right, I shall come to your question. If the frequency with which I revisit a solution versus the time between I last visited the solution and the present time. So there are different versions of what this beta could look like. I'll answer this question that has come up. This is exactly this is a fascinating question about reinforcement learning. That if we don't have a reward or penalty, how do we decide whether we are proceeding in the right direction? This is the concept of exploration, essentially. So what I do is I might be like an entropy function in a way. I try different things. I don't have rewards or penalties coming in right at that minute, but eventually maybe I will have. Eventually. Okay, so initially I might just be exploring the environment without even perhaps being aware of what I'm going to learn or whether is this my goal. I don't know, for example, doing a PhD. I don't have a goal question in mind, so I'm just exploring this big area that is available for me. And then I eventually come to a question. I don't even know at that point whether my question is the right one or not. Isn't it? So it's like in your mind, you unknowingly form these questions or you are made aware of questions. So this is a kind of intrinsic motivation and exploration coming together, and exploitation as well. And we shall always hope that learning never leads to a regret. If I go back to a couple of slides where I mentioned these terms, so it's basically a mix of this that is happening. Exploration, intrinsic motivation, that is, I am curious, I don't know what's happening, let me try a little more, and eventually learning something, and then a trade-off, perhaps stopping sometime or taking a hard decision. There is another question. Right, it is a recursive function. That's it. That's what I mentioned over here. Dynamic programming, it is recursive because you have recurring subproblems. Like for the Fibonacci series example that I gave you, it is recursive. What will be the factor which makes you decide now that the exploration is over? That is where the exploration and exploitation trade-off comes into consideration. It could be, right? It could be, for example, you get tired or this beta factor over here is you become impatient in real life. If I want to draw an analogy of reinforcement learning in real life to real life learning, it could be that I no longer have any motivation left in me. It's all done. I've tried it all, or I could just be tired, or basically, there are, you might have this thing of asking your peers that should I try something else? So there are many, many ways actually to kind of decide. I can't say there is a fixed way of deciding when the exploration is over. It'll depend on the problem that you are trying to solve, rather. Right. So that is why you might have some people who just give up on the very first failure, while there are some people who plod on. Right. So there is this exploitation trade-off that is perhaps a little, what shall I say? People who are more patient, the trade-off is appears at a later stage. So I suppose it's the same to do with an agent. We are all agents in a way, isn't it? So some other important terms, we have Monte Carlo method, where I do a number of trials in order to learn value functions, and I do an average of that. This is a very basic scheme that comes under reinforcement learning, which is I keep trying. I repeatedly do a particular experiment in order to learn values. The Monte Carlo method actually is something that is very, very commonly used in animal experiments, in animal psychology experiments. Since unfortunately we don't understand what animals have to say, so a Monte Carlo method is something that is done over there. You repeatedly give them something to do, and you have a reward sequence happening. For example, you want to train them to train a monkey, say, to observe or to identify a particular color. So you're training a monkey to identify blue. So whenever it touches blue, you give it a grape, and whenever it touches pink, say the other color is pink, you give it a shock, or maybe you don't give it a grape. You give it something that the monkey doesn't like. So what happens over here is you repeat this experiment a large number of times, so then the monkey gets wired to this function, this action function thing happening, that if I touch blue, I'll get a biscuit or I'll get a grape, but if I touch pink, I won't get it. So over here is you don't know the function that is happening. You kind of make up a function on your own, but you see rewards happening and you have an action, right? And so given this, you try to average the action reward thing that is happening, this interaction that is happening, to kind of come to this decision that maybe touching the blue thing is a good way to get along with life. Okay, so Monte Carlo methods are something that animal psychologists use a lot. And then we have temporal difference algorithms, which are looking at local solutions, which again, if you remember that I mentioned over here when I was describing beta, another learning parameter that is coming up, of learning parameter being a function of the frequency of revisiting an action and a reward action reward transition, revisiting that, as well as the time difference between my last visit to it and the current moment. If I want to use that kind of a parameter in my equation, I have something called a temporal difference algorithm. Excuse me. So these are all different strategies that come under the umbrella of reinforcement learning. So I hope this is clear so far. I hope this has been clear so far. Fine. So the primary categories that we have under reinforcement learning are passive reinforcement learning and active reinforcement learning. In passive reinforcement learning, what happens is the policy is fixed. Policy meaning these are the actions, but I have absolutely no idea of what reward function is embedded in my policy. I just know there are rewards. I know there are reward values. Okay, so this transition model or the reward function is I am unaware about it. Meaning that when I do something, I don't know what I will lead to, but then I'll just keep doing certain things in order to eventually arrive at the conclusion that perhaps if I do this, I will do something. I will be gaining something in the end. Yes. Right, that is true. That is true. Theoretically, it is clear. Taking an example would be we will be giving assignments, and there are a large number of assignments in the book itself where uh, uh, it would be good to look at things. If the policy is fixed, then how will the model learn based on rewards? If you recollect what I mentioned about the animal psychology studies, the policy is fixed, meaning when the monkey touches blue or it touches pink, it gets a reward or an electric shock or maybe some food item that the monkey doesn't like. So this action is clear. Right, if I touch blue, this will happen. Or maybe if I have a maze, I'll maybe go to the left or maybe I'll go to the right. I'll just take these steps around me and I will reach somewhere. So this this transition in terms of what I do is available, but what it actually leads to, the semantics of the policy, that is not something that I know. You can walk through. If for one example you can walk through would be helpful in assignment as well. I will do that. I will do that. I will definitely try to do that. Right. The environment, we can assume that the environment is fixed. We can assume that the environment is fixed. But if you actually want an agent to be very effective, you might give it a dynamic environment and allow it to kind of find its own. You have policies fixed over there, right? And the environment is fixed. Yeah, no, in a way we can say that. Yeah, environment is fixed, but I think we can expand this to dynamic environment. We can maybe. That would be an interesting question. Environment is fixed in the sense that I know what, like, if I do this, I will get a reward. But if I put in some new things to explore, right, a new thing to explore. So then what happens is under passive reinforcement learning, there are basically three kinds of techniques that we follow. One is direct estimation, which is like a Monte Carlo method. I keep trying and doing things. One is an adaptive dynamic programming method, which uses the basic policy of dynamic programming. And another thing is the temporal, the temporal difference technique. So the adaptive dynamic program and the temporal difference program, that is something that should be helping in a dynamic environment. That is what I think so. Through if I can design my policies or if I can design my my functions in such a way there is an exploration exploitation trade-off inbuilt within my policy function, then perhaps I can have passive reinforcement learning happening in a dynamic environment. I think so. basically the environment is fixed if I'm doing something like a repeated trial, like for the animal psychology problem, there the environment is very fixed. But then again, what happens over here is what psychologists do, even what we do, even what babies do, is we bring in a concept of attention over here for dynamic environments. So when the environment is fixed, you keep doing something till you get tired and you learn it. But for a dynamic environment, the concept of attention comes, meaning that this is something that has come in right at this moment. So should I try it or not? I know my policy, it is just touching it. Right. So now I will have some reward happening. I will again revisit the solution. I know what I had to learn from my earlier movement. So now if I take a new movement, I will try to find out what is going to happen from there. So I have an adaptive thing happening, meaning I use the same movement, which is I lift my hand up and I touch it in order to explore. So, in my idea, a passive reinforcement learning and active reinforcement learning, the boundary actually is very blurred. This is to my mind. This is how I understand it. We can't actually have two very crisp categories, to my understanding. I think that is possible. Be both active and passive for different subtasks. I think it is possible. I definitely think so. And we say that policy is kind of learning which has been supplied. Right. Uh, actually, a policy is a mapping, right, from a state to an action to the next state. Right. So that is the policy. So now my aim is to maximize the rewards that I gain. So in some cases, I have this fixed that this is the rule that I have to go by. And in some cases, I have to learn through experiments on my own. That is just getting along with the environment and learning things. So at times, this will be supplied by the system builder, and at times it won't. So, like if I take an example of living organisms in the world, you have some policies that evolution has gifted you, and the rest you find on your own. Right? So there is active learning and passive learning happening at the same. A human being will be a mix of everything. It's a mix. A human being, or not only a human being, all living organisms are a mix of everything. You have supervised, you have unsupervised, you have reinforcements happening. At times, you have to behave like a Markov decision model. At times, you have to do that. It's a mix. So, the question that I have at this moment, being someone who is curious about intelligence in nature, is how about bringing all these different models together and then seeing how these different systems interact? Because all living organisms, even trees, they too learn so many things, isn't it? Because trees too learn how to uh, face the sun. That's something that evolution has taught them, but then you will see trees tend to take on peculiar shapes when they grow on. Their transition is very slow. A human being or an active agent like an animal, the transition is very fast. The transition function is very fast. But for a tree, it's very slow. So you have these weird shapes coming up, which again is their learning function, which again is their beta function, their learning parameter. So these are all fascinating things that happen in nature, and it would be great if we could actually see how these different learning mechanisms interact with one another. We don't know, in the days to come, we might even find some other new learning mechanisms coming up. We really never know that. Okay, so now coming on to continuing on from the last slide. Uh, so now, like passive reinforcement learning, that is what I mentioned, that the policy is fixed, the rules are fixed in a way, and but I'm not aware of the semantics that are embedded under this. I don't know what they mean. So I kind of try to form a model of what the world has to offer in my mind through experiments. So this is an example. There's another example. I shall share my slide on that as well. So if I have this policy over here, and I have these two states over here, that if I reach here, I get a reward of +1, and over here, if I come, I get a reward of -1. And the policies are, if I'm at this particular stage, I can just move upwards. If I'm over here, I can only move towards the right. And each of these, they have a reward value attached to it, some kind of a reward value. Like, for example, the monkey problem is whenever it touches pink, it gets a grape. So this is like a reward value, a numerical assumption or a numerical equivalent of that reward. So what I do over here is, for a direct utility estimation method, is I keep revisiting these solutions. I sum them up. I sum up these different reward values, and I keep on taking averages of these values at individual stages, towards the aim of forming this table at the very end of it, which is an average of all the different values that I've accumulated over time when I come to this stage or when I come to this state. I arrive at this table, and then I know that if I have to move from this 1 1 to 4 1, perhaps if I go through this path, it would lead to maximizing my rewards. Because if I go through this path, it's my rewards are going down. Right, so I kind of learn that if I follow this path to here, to this path, I might be maximizing my rewards. That is just kind of forming a trail of sorts of what will lead me to a good thing happening. But the problem with direct utility, I shall take you through this example over here. But the problem with direct utility estimation is, through this averaging thing that is happening, this operation that I'm doing, you see this state over here, which is 3 2 and 4 1. They both lead to this state, right? But they have different values. One has a 0.66 and one has 0.38. So now the problem with this direct utility is the semantics of the reward. Like, why is this value different? Why? What does this difference mean? We really have no way of finding that out. Maybe if I am a semantically active agent, I might be trying to find out in a way that if once I come to this particular state, the reward over here is higher because it takes me to a state with a higher reward value. And over here, I come to a lower value, and over here, I only have one option. That could be one of the semantics. But if I just give you this table over here, and an agent that has no other way of learning the world, it basically loses out on a lot of semantics of the real world, right? Semantics meaning the meaning of what these different values stand for. So in direct, I'll just take you through this example and then show what's happening. So like I mentioned, you have this policy that is fixed. You know the rules of it, and then you execute a series, you calculate the values. Like over here, the reward at these different points are 0.4, and now over here it's 1. So if I take a trial of the form from 1 1 to then 1 2 and 1 3, and I get a reward of 0.4 at each stage, minus 0.4 at each stage till I reach 4 3. So what happens is the total reward for the state 1, comma 1 for the first trial is 0.72 because I sum it all up. Okay. I sum this entire state. For the next trial 2, it will be the same. But for the third trial, it will be different, right? Because I reach from 1, 1. But this again, the ultimate state over here is different. But for 1, 1, what is going to happen is when I'm trying to prepare this table over here, it will find these individual values. After the first trial, it got 0.72. After the next trial, it'll get 0.72. After the third trial, it'll get another value. So after each trial, I'll just replace this value over here with the average of these values. So I have no semantics, right? Right, how we got 0.72, right? So if I add these all up, so it's 1, 2, 3, 4, 5, 6, 7. So it's minus 0.28 and I have plus 1. So 1 minus 0.28 gives me 0.72. So I'm just adding on these rewards, just adding them on. Okay. So I get 0.72 for the first trial. So you see it goes from 1, 1, then it goes to 1, 2, 1, 3. It again comes down to 1, 2. It just tries out things to see what's the best thing, to kind of find out a mechanism to arrive at a better reward value. So again, it tries a second trial and then again a third. So then for all these different values that it gets, it finds an average and it creates this table over here. We just add them up. Over here, it's mentioned that a reward value of minus 0.404 is available for each of these non-terminal states. You see over here, non-terminal states. No discounting, meaning no impatience being added over here. So if I add these different values till I reach the final goal state, which is 4, 3. So from 1, 1, if I follow this trail and I reach 4, 3, I get a reward of 0.78, which is just the sum of these values, these reward values. These are the non-terminal states, right? And the same thing happens for the second trial. And for the third trial, it will be 1, 2, 3, 4. So which is the 0.16 minus 1. So it's going to be 0.84 for this one. Similarly, you see for the state 1, 2, over if I start from 1, 2, from this particular position, which is the second position over here, I get a reward value of 0.76. But if I start from here, I get a reward of 0.84. Right? So again, it happens the same for this. So over here, it is, right, I see 0.76 again. So for each of these trials, for each of these samples, it takes an average of these rewards and it kind of builds this table over here. Fine. I'll show you another example as well. So it adds up these different values for each of these individual states over here that we have, all these different states, and it takes up an average. You see the term over here, a running average for each state. So the aim over here is if this be my utility function, meaning how good my policy is, I'm just trying to find out how good if I follow this kind of a transition from a non-terminal state to a terminal state, is this a good thing to do or not? So I want to maximize this entire transition. Right. So the aim is if I keep adding this up, if I keep doing an average, I will, after infinitely many trials, I will perhaps converge to the true expectation. So I keep trying. At a certain point in time, we will be seeing that the average value no longer changes. Right, after a large number of iterations. So we might come to the conclusion that perhaps if I go from this particular state to any other state, to the goal state, this is the reward that I'm going to get after infinitely many trials. So over here, what is happening is easy to understand in the sense that I keep doing an average of a particular action, right? If I pick up, for example, I'm trying to learn how to pick up a heavy object, your you adjust the force of your hand, you adjust the muscles, or you adjust your placement of the hand, right? So at each placement that you do, you have a reward happening, right? So now for a passive reinforcement learning, what happens is there's nothing new to add on to this. If you place your hand in this way, you get a particular value. If you place your hand in another way, you get another value. Right. So I try these different combinations, and I ultimately, my aim is to arrive at that particular movement. I will come to that. This particular movement sequence that will lead me to pick up a certain object in the right fashion. This is what the aim is. Like I kind of take an average of these values that are happening, but over here, what happens over here is I lose the semantics of the entire connection. Meaning, when I have this kind of repeating things, the values over here, why are they at all different? I have absolutely no clue on that. It's just I've taken an average, and I learned that if I take a path that is through this, my rewards are higher. That's just about it. I don't know the semantics of it. So now, in order to embed the semantics of it into this learning mechanism, we have these other procedures like adaptive dynamic programming and temporal difference. And we'll get back. We'll go to that in tomorrow's class. But for today, I would just like to show you another example of direct utility estimation, which is a smaller. Please give me a moment. Right. Here is another example. So if you see, this is my policy. I go from B to C in this direction, and I go from E to C in this direction, and A in this direction. And the rewards at A and E, these are the two exit states. For D, it's plus 10, and for A, it's minus 10. So now if I move from B to C to D, for B, the value is always an 8. Why? Because from B to C, it's minus 1. From C to D, it's minus 1. And D is a 10. So the entire sum of this transition over here from B to D is an 8 in episode 1. In episode 2, it is 8 again. And so the average of these two transitions for B is 8. So you have a plus 8 over here. For C, what's happening? From C to D, it's 10 minus 1, which is 9. Again, C to D in my second episode, it's 10 minus 1, which is 9 again. Over here, from C to D, it's 10 minus 1, which is 9 again in the third episode. But in the fourth episode, I don't move from C to D. Right. So over here, from C to D, my transition is 0 over there. But from C to A, my transition is minus 10 minus 1, meaning minus 11. So if you recollect again, for direct evaluation, we are not concentrating on the semantics. We're just doing trials and we're adding rewards. So for all these 4 trials that I did, the sum for C is minus 9. Sorry, 9 plus 9 plus 9, 27. And over here, this is minus 11. So it comes down to 27 minus 11, which is 16. 16, and we have 4 trials over here. Right, episode 1, episode 2 can be the same. It doesn't matter. You're just trying out different things. We're just trying out different things. You can have multiple trials with just the same set of moves. It doesn't matter at all. You're just trying to learn values over here. irrespective of the semantics, right? So it doesn't matter. So over here, right. So the values over here, it boils down to 16 because for all these 4 episodes, for these 3 episodes, my value was 9, but over here it became minus 11. So 27 minus 11 is 16 for 4 training episodes. My average becomes 4. So for C, I have the value 4. Sorry, I missed the question that was over there. First 2 episodes are the same. This is a problem with direct evaluation. We are not taking that into account. This is a problem with direct evaluation that I'm constantly saying. It doesn't take the semantics into consideration. It's a very basic, it's a very primitive strategy of reinforcement learning. The strategies that we'll do tomorrow, which is adaptive dynamic programming and temporal difference, they take these state pairs into consideration. This current state and next state pairs into consideration. The formulations do that. Direct evaluation doesn't do that. It's a primitive strategy. It's a basic strategy. And there was this other question, I'm sorry, which I missed about a beta and a gamma. Right, difference between beta and gamma. I'll get back to that. BCD, ECD. There is no particular rule actually over here. There is no rule that is happening as to which trial I should do first and which trial I should do next. There is no such rule in that way. The only information that I have is if I'm at one particular state, what move that I can take to the next state. That's the only information I have. That's all. The reward is over here. If you see, it's a -1, it's a -1. I have those values available with me. I have those values available. Like for the animal psychology problem, it's the grape. So I can equate the grape to a -1, maybe. These are just values that are available to you. So now, since right, it can select randomly. It doesn't matter at all. It's just trying out. You're just exploring the environment over here. You're just trying it out. Right. It doesn't matter which trial comes first, which trial comes next. It doesn't matter at all. Like I mentioned over here repeatedly, that the semantics are immaterial over here. Okay. And the first state is also immaterial over here. In a way, it is a brute force approach, in a way. Perhaps I'm not going through all the different trials, maybe, but maybe if I take the limit to infinity, I will maybe exploring all possible trials, maybe yes. Right, we can do that. There is there is, since the semantics are inconsequential in this particular mechanism, I don't have to repeat episodes. But I keep repeating my transitions from one state to another state. I keep doing that. Okay, so I am in one place. For example, I start at B and I keep moving. So I keep adding them up and I keep doing an average of that. Right, so when I'm at C and I have to move at D, I keep doing that and I keep getting a reward value for that. I add and I average. Like if you see over here, for episode 1, 2, and 3, the transition is from C to D and the sum is always 9, right? But in the fourth trial, it just takes another thing. It moves from C to E. So it kind of does an exploration over there and it tries a new thing. And then the value goes down to -11. So for all these 4 episodes over here, the total value goes down to 16. The sum goes down to 16. Right. But over here, we're not seeing if this is from C to D or this is from C to A. All of that comes up uh, in the next strategy, which is in adaptive dynamic programming as well as in the temporal difference strategy, where that the semantics of every pair of states, which is the current state and the next state. I keep considering these pairs. So now, if I have to embed the semantics into this particular problem, you see, since D leads to a higher reward, it is evident that if I move from C to D, my ultimate value will always be greater. Isn't it? It's evident from there. But since I don't embed it into my learning, I unfortunately have have nothing more to do. So I'll share my other screen. Okay. I'll share my previous screen. Right. So over here, what's happening is, right, I'm just concerned about the state that I'm in. Right. I'm not concerned about the earlier stages. Right. But so what happens is this in a way it reduces to um, what shall I say, a supervised learning kind of a thing. I just have labels of transitions or policies. I call my policies my labels. I just know that I have to go from this state to that state using this kind of a policy, but I'm not aware of anything else. Right? So this kind of boils down to a supervised kind of a mechanism. Right? So now, because what I do over here is I don't embed the model that I have learned. I don't embed it anywhere over here in my utility function. This S comma S star, S bar, if S bar be my next state, I don't embed it into my utility function. So if I do something like that, where I embed my learning of the current model into this equation, into my learning the utility function equation, I possibly have a better way of getting along with the environment. So once I embed the gamma over here is essentially the beta parameter that I've been describing in the earlier slide. I took these equations from two different sources, so the notations are different, but they mean the same. The beta and the gamma over here is a discount factor or the impatience factor. And in certain other, in the temporal difference strategy, the gamma over here, it takes into consideration the learning parameter in the sense of the frequencies with which I revisit a particular problem or revisit a particular state action transition, and the distance or the time difference between my last visit and or the last recall and the current time. Right. So once I come to this kind of an equation where I take the reward of my current state as well as values from the states that I have visited starting from S, then I have a more adaptive learning that is happening, isn't it? I suppose that is clear, isn't it? So this is reminiscent of Bellman's equation of optimality, isn't it? Where I was taking, if I go back to this slide, I was trying to maximize the reward of my current state and the reward that I get from my transition. So essentially, this function and this function, there is a similarity in it, isn't it? So this is a more adaptive way, and we come to these new methods of adaptive dynamic programming and temporal difference. So essentially, what we were doing in direct utility estimation, this was a model-based kind of mechanism, right? I'm trying to kind of form a representation of the model in my mind. With these two, which is adaptive and temporal difference, this is a model-free kind of a mechanism. Because in these two mechanisms, I kind of embed the model of the environment within my equation itself over here, right? So in the earlier situations where I am trying to uh, kind of just focus on reward values over here. Here I'm trying to embed the semantics of the model or semantics of the environment into my learning. So this, I suppose, is so these two strategies, which we'll be describing, which we'll be going through tomorrow, are far more better approaches. The direct utility estimation, in fact, is a very slow way of learning things. You have to do infinite number of trials. Only then maybe will you get an idea of what things. If you kind of do infinite number of trials, a large number of trials, then perhaps you will arrive at a convergence. Um, there is this nice video over here which I can show you actually, where they have large number of trials. I hope everyone can see this. This is a fantastic example. That was just on first policy. So now we have 10,000 data points, 10,000 trials. So for the last example, then the number of data points were huge, the number of trials were huge, right? So it kind of converges. One can never say that I will always learn the optimal policy. I can never confirm that. I can never establish that I will learn the best policy. But you will perhaps get a hang of it. You might do better. Right. For example, if I have to, for this particular learning to fly problem, there are going to be negative rewards for actions like wobbling, actions like where I'm not balanced properly. There will be negative rewards for that. And when I actually move up with no wobble, so each of these movements is going to be a data point or an action, sorry, transition happening. So if I can set up these values correctly for the model to train on, for the model to try out its different episodes and learn, then perhaps I could arrive at some kind of a convergence on what is to be done. So essentially, since I am adding values to these different transitions, I am kind of supervising the learning, if you think about it. I'm not explicitly maybe giving label data in that fashion, not explicitly, but I'm implicitly doing it. I am putting these values for this agent to learn through its interactions. So this is what direct estimation is all about. So I do hope it makes sense in some way. I do hope it does. Actually, the gamma that tends to zero, will that be the case? If I look at my, because over here gamma, the value of the impatience factor lies between 0 to 1. If I go to this, it lies from 0 to 1. The convergence comes actually when two states or when two transitions, I see the values are no longer changing, when I have kind of gained an understanding of things. Keep repeating and I ultimately learn, isn't it? I keep repeating something and then you learn that this is how it's supposed to be. So, this is a very basic strategy, a very basic way. And this is primarily used in animal psychology, just as I mentioned, since we don't know how animals, how we can actually get our meaning across to animals, unfortunately. So that's how it is. Oh, I suppose it's 9:30 almost, and you must be getting ready for the next class. But if there are any questions on, I shall be sharing the slides with everyone as well as the resources slide. We can, is it possible? I think so. I think it is. Can you share assignment now so that we can relate class teaching with assignment? I can ask the TAs if the teaching assistants if they can help us with that. Can you share slides? Okay, I could do that. I could try doing that. Can sharing slides. If once I get my slides ready, I think I could share the slides with you. Maybe I could do that. I shall try. I won't commit on it because I may not always have my slides ready, but I will definitely try to share them before the class commences. Sharing, right, I would try to do that. Whenever I get things ready, I shall definitely try to share that. And I will be sharing the resources slides with you. So I would encourage everyone to go through the lectures that are there, go through the literature that is available, and then let's see if we can take this forward. And I really look forward to learning from you actually, because your questions allow me to think. And if any one of you has actually worked with reinforcement learning, I would love to hear from them. I would love to do that. Yeah. I shall talk to my teaching assistant so that they can help with posting assignments early. I shall definitely talk to them about that. Yeah. So I suppose it's 9:30 already, and you will have to move along with your other classes. So if there are any questions with regards to whatever the little that we have done today, please do share your questions tomorrow. Tomorrow there will be a small quiz which is from 9:05 to 9:30. I understand that thoroughly. So from 9:05 to 9:30, we'll have a small quiz tomorrow, just a basic quiz, right, on whatever little that we have done today. Just kind of testing, like, in a way, these quizzes kind of not only allow you to think about the problem, they also allow us to think about problems. I thoroughly understand. We are all working and we are all very busy. I do understand that. I think yes, Shivika was there. Shivika, the teaching assistant who was in the class, she has taken attendance. I'm sure about that. Yeah. So if anyone has any questions, we can discuss it in the next class, which is tomorrow. So, right, please feel free to log out and get along with the next class. Thank you. Thank you so much for coming. And let's see how it goes tomorrow. Yeah. Thank you. Thank you so much. Thank you. Have a lovely day ahead. Have a happy day. Yeah. Bye bye. Thank you.